Deep in the southern sky, roughly 163,000 light-years from Earth, there exists a place where stars are being born at a rate so violent, so extreme, that astronomers struggled to believe what they were seeing when they first pointed their telescopes toward it. This is the Tarantula Nebula, and at its heart lies something that defies everything we thought we understood about stellar nurseries. R136A1. A name that sounds like a serial number. Cold. Clinical. But what it represents is anything but ordinary. When scientists first measured this object, they had to check their instruments. Then check them again. Because the numbers coming back seemed impossible. A star with a mass exceeding 250 times that of our Sun. A luminosity so intense it outshines our entire solar system by nearly 9 million times. To put that into perspective, if you replaced our Sun with our 136A1, the Earth would be vaporized almost instantly. Not burned. Not scorched. Completely and utterly erased from existence. But here is where things become truly strange. Stars this massive should not exist. The physics we understand, the models we have built over decades of research, they all tell us there is a limit. An upper boundary to how large a star can grow before the pressure of its own radiation tears it apart. That limit was believed to be around 150 solar masses. Our 136A1 ignores that limit. How? The answer remains one of the most heated debates in modern astrophysics. Some researchers believe these monsters form through collisions, smaller massive stars smashing together in the crowded chaos of dense stellar nurseries. Others argue that under the right conditions, with the right composition of gas and dust, nature can simply break its own rules. The Large Magellanic Cloud, this irregular dwarf galaxy orbiting our Milky Way, has become a laboratory for understanding the most extreme processes in the universe. And the Tarantula Nebula sits at the center of it all like a beating heart pumping new stars into existence at a furious pace. 30 Doradus. That is another name for this region. Named after a constellation visible only from southern latitudes, it spans nearly 1,800 light-years across. If it were located as close to us as the Orion Nebula, it would cast shadows on Earth. You could read by its light at midnight. But distance is deceptive in space. What appears as a faint smudge to observers in Chile or Australia is actually one of the most luminous and productive star-forming regions in our entire galactic neighborhood. Within the tarantula, over 800,000 newly formed stars burn with the blue-white intensity of extreme youth. Many of them will die spectacular deaths within just a few million years, their lives measured in cosmic eye blinks rather than the billions of years our Sun enjoys. The cluster R136, where our impossibly massive star resides, contains at least a dozen stellar giants exceeding 50 solar masses. Together, they generate stellar winds so powerful they are literally reshaping the nebula around them, carving cavities and pillars in the surrounding gas like sculptors working in cosmic clay. These winds carry material outward at thousands of kilometers per second. Not per hour. Per second. Particles accelerated to speeds that would cross the distance between New York and Los Angeles in roughly 2 heartbeats. And when these stellar behemoths finally exhaust their nuclear fuel, they will not fade quietly into the night. They will explode. The supernovae produced by stars like our 136A1 release more energy in a single moment than our Sun will generate across its entire 10 billion year lifespan. These explosions seed the surrounding space with heavy elements, the iron in your blood, the calcium in your bones, the gold and jewelry worn around the world, all of it forged in the death throes of massive stars. But there is another possibility. One even more dramatic. Stars above a certain threshold may not produce ordinary supernovae at all. Instead, they might undergo something called a parent stability supernova, a runaway thermonuclear detonation that tears the entire star apart, leaving nothing behind. No neutron star. No black hole. Just an expanding shell of debris carrying the building blocks of future worlds. The Tarantula Nebula has already witnessed such violence. Supernova 1987A, the closest observed stellar explosion in nearly 4 centuries, occurred in this very region. Its light reached Earth on February 23 of that year, and for a few weeks, a single dying star shone brighter than 100 million of its neighbors combined. Astronomers worldwide turned their instruments toward the event. What they witnessed rewrote textbooks. Neutrino detectors on opposite sides of the planet registered particles from the explosion almost simultaneously, confirming theories about how massive stars collapse. The shock wave, still expanding today, continues to provide insights into physics at energy scales impossible to reproduce in any laboratory on Earth. But 1987A was just the beginning. The tarantula is preparing to give us more. With so many massive stars approaching the ends of their brief lives, astronomers estimate that multiple supernovae will occur in this region over the coming millennia. Some models suggest we could witness another within our lifetimes. Perhaps even within the next few decades. Imagine watching in real time as a star millions of times brighter than anything in our sky tears itself to pieces. Telescopes across every continent pointed at a single point of light growing brighter day by day, hour by hour, until it rivals the full moon in brilliance. This is not fantasy. This is prediction based on careful observation and stellar evolution models refined over generations of scientific effort. The James Webb Space Telescope has already turned its golden mirrors toward the tarantula, capturing images of unprecedented detail and clarity. What it revealed startled even the researchers most familiar with this region. Thousands of young stars previously hidden behind curtains of dust suddenly became visible for the first time. Protostellar jets shooting material across light-years of space. Dense knots of gas on the verge of collapsing into new stellar systems. The entire process of star birth laid bare in infrared wavelengths that pierce through obscuring clouds like X-rays through flesh. One particular image shows what appears to be a cavity in the nebula, a bubble carved by radiation pressure from the central cluster. Inside this bubble, wispy filaments of gas glow with the light of elements excited by ultraviolet radiation. Hydrogen, oxygen, sulfur. Each emitting at characteristic wavelengths, painting the scene in colors no human eye could ever see directly. The structure resembles something organic. Biological almost. As if the nebula itself were alive, breathing, growing, consuming the raw material of the universe and transforming it into something new. Perhaps in a metaphorical sense, it is. Star-forming regions like the tarantula represent the generative engine of galaxies. Without them, no new stars would ignite. Without new stars, no planets would form. Without planets, whatever miracle of chemistry and circumstance produces consciousness would have nowhere to unfold. Every atom heavier than hydrogen and helium in your body passed through at least one stellar furnace. Some passed through several. The carbon in your DNA might have originated in a red giant that exhausted its hydrogen billions of years ago. The oxygen you breathe with each breath could have been expelled in the outer layers of a dying star before our sun even existed. We are, in the most literal sense possible, connected to places like the Tarantula Nebula. Our material heritage includes the deaths of countless stars whose names we will never know, whose light reached Earth long before any human walked its surface. This realization transforms how we look at these distant cosmic nurseries. They are not merely objects of scientific curiosity. They are our origins made visible across vast stretches of spacetime. The Large Magellanic Cloud itself has a story worth telling. For most of human history, only those living in southern latitudes knew of its existence. A fuzzy patch in the night sky, seemingly separate from the band of the Milky Way stretching overhead. Indigenous peoples of Australia, South America, and Africa incorporated it into their mythologies, their navigation systems, their calendars. When Ferdinand Magellan's expedition circumnavigated the globe in the early 16th century, European observers finally documented what others had known for millennia. The cloud took on the name of the explorer, though he never completed the journey himself, killed in the Philippines months before his ships returned to Spain. For centuries afterward, the nature of this object remained mysterious. Was it a cloud? A cluster of stars? Something else entirely? The answer came slowly, piece by piece, as telescopes improved and astronomical techniques advanced. In 1912, Henrietta Swan Leavitt made a discovery that would revolutionize our understanding of the cosmos. Working at Harvard College Observatory, studying photographic plates of the Large Magellanic Cloud, she noticed something remarkable about a class of stars called Cepheid variables. These stars pulsate. They brighten and dim with regular periods ranging from days to weeks. What Leavitt found was a relationship between how long each pulsation cycle lasted and how intrinsically bright the star truly was. This period luminosity relationship became one of the most powerful tools in astronomical history. By measuring the period of a Cepheid variable anywhere in the universe, astronomers could calculate its true brightness. Compare that to how bright it appears in the sky, and you can determine its distance. Using Leavitt's discovery, Edwin Hubble later proved that the Andromeda Nebula was actually a separate galaxy far beyond our own Milky Way. The universe expanded from a single island of stars to a vast cosmic archipelago containing billions of galaxies. All because of careful observations of the Large Magellanic Cloud. Today we know this satellite galaxy contains approximately 30 billion stars. It orbits the Milky Way at a distance of roughly 160,000 light-years, gradually being pulled closer by gravitational forces. Computer simulations suggest it will eventually merge with our galaxy, though the timescale stretches across billions of years. When that merger occurs, the Tarantula Nebula and its stellar progeny will become part of our own cosmic neighborhood. Stars born in that distant nursery today will have lived their entire lives and died long before the collision completes, but their descendants, the elements they created and scattered, might someday become part of planets orbiting stars that do not yet exist. The universe operates on timescales that dwarf human comprehension. We measure our lives in decades. Stars measure theirs in millions or billions of years. Galaxies measure theirs in tens of billions. Yet somehow, through instruments of glass and metal and silicon, through mathematics refined over centuries, through the accumulated effort of countless researchers building upon each other's work, we have managed to peek behind the curtain. What we see there is simultaneously humbling and exhilarating. Humbling because the cosmos cares nothing for our existence. Stars ignite and expire without regard for whether anyone observes them. Galaxies collide without permission or purpose. The universe simply is, operating according to physical laws indifferent to human concerns. Exhilarating because we can understand it anyway. The same laws that govern particle interactions in laboratories on Earth govern the fusion reactions powering stars halfway across the galaxy. Mathematics developed to solve practical problems centuries ago describes the curvature of spacetime around black holes. The periodic table assembled through painstaking chemical experiments explains why stars shine and why nebulae glow in the specific colors they do. There is a deep unity underlying the apparent chaos of the cosmos. And studying places like the Tarantula Nebula helps us recognize that unity more clearly. Consider what it means for a star to have 250 times the mass of the Sun. Our Sun contains about 330,000 times the mass of Earth. Everything in our solar system combined, all the planets and moons and asteroids and comets, amounts to less than 0.2% of the Sun's mass. Jupiter, the largest planet, could fit inside the Sun over 1,000 times. Now multiply all of that by 250. Our 136A1 could swallow the orbits of all our planets without disturbing its outer layers. From a hypothetical planet orbiting at the distance Earth orbits the Sun, this stellar monster would fill most of the visible sky, a wall of blazing plasma where no solid world could possibly exist. But such a planet could never exist in the first place. The radiation environment near stars this massive would sterilize any rocky body almost immediately. Ultraviolet light intense enough to strip atmospheres. X-rays capable of penetrating deep underground. Stellar winds so dense they would sandblast exposed surfaces. Life as we understand it requires a gentler host. Smaller stars. Cooler stars. Stars that burn steadily for billions of years rather than blazing through their fuel in a few million. This is another reason why the tarantula fascinates researchers studying the possibility of life elsewhere in the universe. The conditions that produce monstrous stars like our 136A1 also produce countless smaller siblings. Within the same nebula, alongside the hypergiants and supergiants, thousands of modest stars comparable to our Sun quietly gather mass and begin their long, stable lives. Some of these younger stars undoubtedly possess protoplanetary disks, flattened rings of gas and dust where planets are currently forming. The same processes that built our world 4.6 billion years ago are repeating themselves right now in the tarantula. Give these systems a few billion years. Allow planets to form, cool, develop atmospheres. Add water delivered by cometary impacts. Stir in the complex chemistry that arises when energy flows through chemical gradients. What emerges? We do not know. Perhaps nothing. Perhaps something utterly alien to our experience. Perhaps something surprisingly familiar. The one certainty is that the raw materials exist. Carbon and oxygen and nitrogen and all the other elements essential for biochemistry as we understand it are present in abundance, forged by earlier generations of stars and now cycling through new stellar generations. If life is common in the universe, the Tarantula Nebula will eventually host it. If life is rare, this region might remain forever sterile despite its fecundity. Either answer would be profound. The search continues. Every new telescope launched, every new instrument deployed, every new observation completed adds another piece to the puzzle. We are assembling a picture of cosmic evolution from the Big Bang to the present day, and stellar nurseries like the Tarantula occupy a crucial chapter in that story. Without star formation, the universe would consist only of hydrogen, helium, and trace amounts of lithium. No planets. No chemistry. No possibility of observers wondering about their origins. The violence of stellar birth and death created the conditions for our existence. We are quite literally children of the stars, temporarily organized collections of stellar debris contemplating our own origins. This realization has only become possible within the last century or so. Previous generations could marvel at the night sky but lacked the tools to understand what they were seeing. They invented myths and gods and stories to explain the lights overhead, never suspecting that those lights were nuclear furnaces burning across unimaginable distances. Now we know better. And that knowledge does not diminish the wonder. If anything, it amplifies it. Knowing that the fuzzy patch visible from the southern hemisphere contains billions of stars, knowing that within it lies one of the most extreme objects ever discovered, knowing that the elements in our bodies trace ancestry to similar stellar furnaces, this transforms casual stargazing into something approaching reverence. The universe is not just large. It is generative. Creative in a non-intentional sense. Physical laws operating blindly over billions of years produce complexity, structure, beauty that no designer could match. Spiral arms sweep through galaxies, triggering waves of star formation. Supernovae scatter the periodic table across parsecs of space. Gravity gathers scattered atoms into new stars and planets. Chemistry assembles those atoms into ever more elaborate molecules. Eventually, somewhere, somehow, molecules that copy themselves appear. Evolution takes over. Complexity increases. Awareness emerges. And then, against all odds, the universe begins to understand itself. This is what we see when we look toward the Tarantula Nebula. Not just gas and dust and nuclear reactions. Not just spectra and measurements and data points. We see our past and our future intertwined. We see the fundamental processes that made us possible still operating today, preparing new generations of stars and perhaps new opportunities for life to arise. We see ourselves reflected in the cosmos, tiny and transient yet somehow capable of comprehending the immense machinery surrounding us. The tarantula will continue forming stars long after every human currently alive has returned to dust. The Large Magellanic Cloud will continue orbiting the Milky Way until gravity pulls them together in a cosmic embrace. The universe will continue expanding, cooling, evolving according to principles we have only begun to grasp. Our window of observation is brief. A few thousand years of recorded history. A few centuries of scientific astronomy. A few decades of space-based telescopes revealing wavelengths invisible from Earth's surface. In that narrow window, we have learned astonishing things about our place in existence. And we have recognized how much remains unknown. Every answer generates new questions. Every discovery reveals new mysteries. The universe is not running out of secrets to share. We are only just learning how to ask the right questions. And places like the Tarantula Nebula, spectacular and violent and creative beyond measure, remind us why those questions matter. They matter because understanding the cosmos means understanding ourselves. They matter because the journey of discovery is one of the most meaningful activities available to our species. They matter because out there, 163,000 light-years away, stars are being born right now. And somewhere, eventually, perhaps one of those stars will warm a world where other minds look up at their own night sky and wonder about the distant lights they see there. Perhaps they will notice a faint spiral smudge and wonder what lies within it. Perhaps they will develop their own mathematics, their own telescopes, their own burning curiosity about the nature of existence. And perhaps, in some distant archive, evidence of our own wondering will still persist. Radio signals propagating outward at the speed of light. Spacecraft carrying golden records into interstellar darkness. The accumulated knowledge of our civilization encoded in electromagnetic whispers spreading ever thinner across the void. We may never meet those hypothetical observers. The distances are too vast. The timing too improbable. Two civilizations separated by thousands of light-years and millions of years might as well exist in separate universes entirely. But the connection remains. The same physics. The same chemistry. The same fundamental forces shaping matter into stars and planets and, occasionally, into beings capable of asking why. When you look at the Tarantula Nebula through a telescope or gaze at photographs captured by instruments orbiting high above our atmosphere, you are looking at a mirror of sorts. A cosmic mirror reflecting processes that occurred here, around our own sun, billions of years before the first fish crawled onto land. The nebula does not care that you are watching. The stars within it burn regardless of observation. The universe proceeds indifferent to whether anyone notices its workings. But you notice. And that noticing, that capacity to observe and wonder and understand, might be the rarest phenomenon in all of creation. Rarer than hypergiants. Rarer than supernovae. Rarer than the peculiar conditions that allow galaxies to form in the first place. Consciousness examining its own origins. The universe waking up to itself. This is what the Tarantula Nebula truly represents. Not just a stellar nursery. Not just an astronomical curiosity. But a reminder that we are participants in something vast and ancient and ongoing. The stars being born today in that distant cloud will shine for millions of years. Some will die violently. Others will fade slowly. All will contribute their substance to future generations of stellar evolution. And somewhere, somewhen, the chain of cause and effect that connects those newborn stars to observers not yet born will continue unbroken. Hydrogen becoming helium. Helium becoming carbon. Carbon becoming life. Life becoming awareness. The story never truly ends. It only transforms. 163,000 light-years away, the Tarantula Nebula continues its ancient work. Creating suns. Forging elements. Preparing the raw materials for worlds and wonders we cannot begin to predict. All we can do is watch. And wonder. And remember that we are part of this same grand process, temporarily assembled from stellar ash, briefly aware, profoundly fortunate to exist at all. The cosmos gave us eyes to see it. The least we can do is look.